All right, so now let's talk about disaccharides. Disaccharides are when you have two monosaccharides linked together. Lactose is a famous one. Lactose consists of both beta-galactose and alpha-glucose. And they get linked together by a glycosidic bond. Okay. If we look at this disaccharide of lactose here, there's a few important features that this is what our focus is going to be. So again, this is lactose, and in particular, it's alpha lactose, because on the free anomeric carbon, the OH group is pointed down, so it's the alpha isomer. Okay, so that's going to be an important thing. Can we spot whether it's the alpha or the beta isomer? In this case, this is alpha lactose. The other thing that's going to be really important is the glycosidic bond, which is here, okay? This is a beta glycosidic bond because the anomeric carbon, or what was formerly the anomeric carbon, was the beta isomer. That OH group is pointed up. Notice that the hydrogen's pointed down, so that was the beta isomer. And it's a 1,4 linkage because it's between carbon 1, the anomeric carbon, always be between carbon 1. And then in this case, the other sugar is connected at carbon 1, 2, 3, 4. So this is a beta 1,4 glycosidic bond. Okay, so this is two main skills that we're going to need to be able to develop for talking about disaccharides. Is it the alpha or the beta isomer? Again, we're going to look at the free anomeric carbon to figure that out, and then characterize the glycosidic bond as being alpha or beta, and then between which carbons. In this case, it's carbon 1 and carbon 4. Okay, so there are three famous disaccharides that we just got to know what they're made of, okay? Maltose is made up of 2 molecules of glucose. Lactose is made up of glucose and galactose. And sucrose is made up of glucose and fructose. All right, again, I don't love memorization, but I've seen on the ACS exam a question like, sucrose is made up of which 2 monosaccharides? So these 3 disaccharides in particular, we just got to know the building blocks for them. Notice that glucose is involved in all of them. And then the difference, maltose has another glucose, lactose has a galactose, and sucrose has fructose. Okay, flashcard it, do whatever you got to do, but those are things that we just have to know. Okay, there are many other disaccharides. These are just the 3 most important ones, the 3 most common ones. Maltose. So maltose is what's known as malt sugar. So especially it's used very often in cereals and candies, as well as brewing beer. So the malt that you use to brew beer is actually maltose. And it's composed, as we said, of 2 molecules of D-glucose. It also turns out that if you take a large polysaccharide and you digest it, the most common sort of intermediate before it gets broken into all the little tiny monosaccharides is the disaccharide maltose. So we're going to talk about a lot of polysaccharides here in the next lecture. And when they get broken down by our body or even by plants, they get broken down first to maltose and then to glucose. And it's found in both the alpha and beta form, which again corresponds to where's the OH group on that anomeric carbon. Maltose, so this is another thing we just have to know, is linked by an alpha 1,4 glycosidic bond. Okay, so what does that mean? That means that the anomeric carbon that has the hydroxyl group that's going to form the glycosidic bond is in the alpha conformation. That's what this portion is telling us. Alpha 1, meaning the anomeric carbon, is going to have the OH group in that alpha, meaning pointed down form. okay? Remember, both forms of alpha and beta glucose exist in your body. But if your body's gonna go and make maltose, what it's gonna do is only selectively grab that one alpha isomer. That's the only one it would know how to use in order to make this particular disaccharide. The 4 comes from the fact that you're forming this glycosidic bond between the OH group on carbon 4 of the other sugar, which is in this case also glucose, right? So we have alpha glucose, and this one, it wouldn't matter if it was alpha or beta. Okay, so this one has to be alpha. That's how we get the alpha 1,4 bond. This one could be alpha or beta. It would just depend on which isomer of maltose you got, right? So if I started out with my second sugar as alpha glucose, I would get alpha maltose. If I started out with beta glucose as my second sugar, I would get beta galactose or beta maltose. And those are in equilibrium with one another. The fact that this hydroxyl group right here is pointed down, well, that's just something that's unique to glucose. Remember that the position of the hydroxyl groups on carbons 2, 3, and 4, that's just set by the identity of the sugar. If this was galactose, it wouldn't be pointed down, it would be pointed up for carbon 4, right? But because this is glucose, that OH group is pointed down on carbon 4. And that's just glucose being glucose. That's the identity of glucose, okay? So these two will form one of those glycosidic bonds, which again, if we were in organic chemistry, we would just call an ether. But here we're going to call it a glycosidic bond, okay? And again, this would be now alpha maltose, which is this disaccharide. Again, characterized by this alpha 1,4 glycosidic bond, which means that our anomeric carbon is in the alpha position, and the other side of that bond, the 4, is because it's the 4th carbon on that second monosaccharide. Okay, and this is the alpha isomer because that OH group's pointed down. It would be in equilibrium though with the beta isomer, so we can change this around and also get beta maltose by switching the position there. This would now be beta maltose. Okay, so one of the things that we just have to know is that maltose has an alpha 1,4 glycosidic bond. Lactose. Lactose is that disaccharide primarily found in milk, both in human breast milk, but also in cow milk. People are lactose intolerant because we all have the gene to be able to digest lactose. In some people, it gets like turned off as they develop into adulthood, and in other people, it doesn't. So some people are able to digest lactose into adulthood, and other people aren't. Okay. All right, so let's see if given what we see here, we can't figure out the type of bond, the type of glycosidic bond that's in lactose. Okay, this is again something that we just got to know. Let's see if we can't figure out what's going on. So first of all, the first component of lactose is going to be beta galactose. Which direction will my hydroxyl group be pointed if it's beta galactose? All right, so that should be pointed up for beta galactose. And my glycosidic bond's going to be formed here. So here's what I'm looking at. So let's see if we can't classify this. Again, we said that our anomeric carbon was in the beta form. So this is going to be a beta glycosidic bond. And it's specifically going to be, so this is carbon 1, as it always is. And then 1, 2, 3, 4. So this is going to be a beta 1,4 glycosidic bond. Okay. Again, I got the beta 1 from the fact that my anomeric carbon in that first unit has its OH group pointed up on that anomeric carbon. and it's the other component is the OH group on carbon 4. The fact that it's pointed down is just because that second sugar is glucose, right? So I don't know, based on the beta 1,4, what direction that OH group is. I know based on the identity of the sugar, the fact that that OH group is pointed down. Okay, so one of the things we just got to know is lactose is connected by a beta 1,4 glycosidic bond. And one of the reasons that I introduced that concept this way is because one of the skills that you want is, if I say, here's a disaccharide you've never seen before, what is the glycosidic bond? You're going to want to be able to tell me it's a, in this case, beta 1,4, just by looking at the structure. Okay, and now sucrose consists of glucose and fructose. Glucose is going to be the first unit, fructose the second unit. What's kind of weird about fructose, let's actually look here. It's an alpha beta 1,2 glycosidic bond. So what the heck does that mean? It means that we started out with alpha glucose, right? And I know it's alpha, let me actually color code things here. Alpha D-glucose, and I know it's alpha because that OH group on the anomeric carbon is pointed down. But for fructose, I'm starting out with beta fructose, and that's important because notice that it's the hydroxyl group on both anomeric carbons that's combining. So that's why I have to have this specification of alpha beta, not just alpha or just beta, because both of the anomeric carbons are the hydroxyl groups on the anomeric carbons are involved in this type of linkage. So it's alpha glucose, but beta fructose. And remember, because fructose is a ketose, because fructose is a ketose, the anomeric carbon is actually carbon 2, not carbon 1, like it is in our aldoses. Okay, so this is an example of the alpha beta 1,2 glycosidic bond for sucrose. Again, to pick it all apart, here's the alpha. It's pointed down on the one unit, which is glucose, and then it's pointed up on the other anomeric carbon, which is the originally fructose. So this is an alpha beta 1,2 glycosidic bond. And notice that this is now our first example of a non-reducing sugar, because neither anomeric carbon has an OH group anymore. Those two anomeric carbons, OH groups, have been joined together. So this would be a non-reducing sugar. Yeah, so this is saying exactly what I just said. Cannot be oxidized using Benedict's reagents. And really what it means to be the fact that there's not an anomeric hydroxyl group on any anomeric carbon is it's not in equilibrium with its open chain form at all. It's locked into those two closed chain forms. Table sugar is sucrose. Okay, so identify the monosaccharides in each of the following: lactose, maltose, and sucrose. Remember, these are just something that we have to know. We have to know that lactose consists of alpha glucose and beta galactose. Maltose is all alpha glucose, and sucrose is alpha glucose and beta fructose. So the good news is that the glucose in each of them are the same. Alpha glucose, alpha glucose, alpha glucose. The difference, lactose contains galactose, and that's actually going to be beta galactose. And sucrose contains fructose, and that's going to be beta fructose. All right, so now given this new disaccharide that we've never seen before, we want to figure out what the units are. We want to figure out what type of glycosidic bond it forms, and then we're going to identify whether we have the alpha or the beta structure of, what is this, Melbiose? I don't know. Okay. As far as A goes, this would involve your constants page. And so one of the things that you would have done before, I don't remember if it was the last lecture or the one before, but was to take all of these Fisher projections and to convert them into Hayworth projections. Okay, so judging by those Hayworth projections, you would go through and look and try to classify each one of these. The big giveaway, so first of all, they're both 6-membered rings, right? If we're looking at carbon 4 in particular, in this one, it's pointed up. So this would be galactose. And in this one, it's pointed down. And that's the big difference between glucose and galactose. So this would be glucose. That isn't something that I expect you guys to have memorized. I do expect you to be able to figure it out based on this constants page that's given. And again, if I gave you a new sugar, mannose or something like that on this sort of thing, you should be able to convert it to the Hawthorne projection and then be able to identify whether or not it was one of those units by matching which direction the OH group is pointed on each carbon. Okay, so galactose and glucose. Characterizing the bond. This is kind of, I think, one of the more important aspects of this particular lecture. So carbon 1, my anomeric carbon on galactose, is it in the alpha or the beta position? This would be the alpha position of that hydroxyl group on galactose. So we can even specify that we got alpha, well, and D, alpha D galactose. And then for the other one, for our other unit of glucose, 1, 2, 3, 4, 5, 6, it is on the 6th carbon. So this would be an alpha 1, 6 glycosidic bond. And then lastly, do we have the alpha or beta Melbiose? Again, I'm going to look at that free anomeric carbon, or the anomeric carbon that has that free OH group. That's also pointed down. So this would have been alpha D glucose as well. So this would be the alpha, or alpha Melbiose. I feel like I've said it differently every single time. Whatever. All right, so to answer the questions, again, we identified this as an alpha 1,6 linkage. We have the alpha isomer of our disaccharide, and the 2 units were alpha D galactose and alpha D glucose,